Hi, everybody. It is Tuesday, January 31st, and this is the first class for our Module 2. I am here in room Z341 if anybody's around and wants to join in person. Otherwise, I assume you're joining online. You can always watch this later. It'll always be up there, but the plan here is today I'm going to kind of take you through the module and the things that you will need to know, and then the basics, and then tomorrow we'll really start focusing on this drawing structures part, which is probably the most difficult piece of the module. All right, so I'd like to start, assuming everything is coming through okay. Yeah, okay, looks like it's good. I'd like to start by just looking at the post on Teams that goes through all the objectives. So there are a couple main objectives for this module. We want you to be able to describe the structure of atoms and molecules. And when I say describe, I specifically mean something. I mean, we're going to go into it, but I mean, be able to determine the number of particles in different atoms. Then we're going to use these structures to draw molecules. We're not going to do that today. We'll start that tomorrow. And then we will balance some chemical equations and talk about some chemical reactions and equations, and that will be a big part of the lab tomorrow as well. All right, so one thing that's a little different about this module from the last one is this is much more kind of traditional chemistry content. So, being able to do some things with atoms and molecules. Some of you may have already learned this, and remember the goal of this course is that you learn new things. So if you kind of say like, oh yeah, I had chemistry a couple years ago, I already know this stuff. That's great. I'm glad you know it, but that doesn't mean that you shouldn't do stuff that you shouldn't learn more this week. So for example, there are two sort of levels of learning about the structure of atoms and molecules. If you go through that initial atoms activity that's shown here, and you realize like, oh, I did this before, I already know this, certainly review it, but then don't just not do anything this week. Let's learn a little bit more in detail, a little bit more in depth about the structure of atoms. So go to the second link and start reading some of that information. And if you already have a good basis in the basics of atomic structure, then you'll probably find that other one interesting. If neither of those appeal to you, then come see me or email me or message me on Teams, and let's talk about what else you can do to engage with the ideas about how matter is constructed during these couple weeks. All right, so that's the idea. Yes, you want to be able to meet objectives, but you also need to be learning new things. So if you had already done this from a previous class, I still want you to do more and learn some new things. All right, so let's talk about that first one, the atoms activity. I copied it over here. So this is going to be the first in several of these style of activities that we're going to do this semester. They look like just kind of a standard worksheet, but they're a little bit different. The reason they're a little bit different is that the goal of these types of activities is to actually have you create the knowledge yourself as you're working through it, rather than reading some information and then practicing or like trying to memorize that information. So these activities always start with some sort of a diagram or a table or some sort of data that doesn't really make any sense at first. So here you can see some pictures of some atoms. We only know that they're atoms because it says in the caption that this is schematic diagrams for various atoms. We know that there are some things called protons, neutrons, and electrons inside there. We know that the protons are positive because it says that. Neutrons are no charge, electrons are negative. And we know what they look like in the diagrams because they're either fully shaded, half shaded, or unshaded circles. From just that little bit of information, we can start making some sense of these diagrams, but there's some other stuff that still definitely doesn't make sense. For example, what is the symbol in the upper right-hand corner? Why does the number change? Why does this one have a plus sign? What are these numbers down here that say AMU? what's the difference between hydrogen and hydrogen ion? So all of these things, we still have questions on that. And the idea is that this activity kind of leads us through that information. And for a lot of people, it ends up really helping them to learn it more completely and more permanently than if they were to just read like a traditional textbook that just explained things. So let's practice. Let's go through this and kind of see what we're talking about. So if you move on to the next page, you'll see some critical thinking questions. Look at the schematic diagrams for carbon. What do all three carbon atoms and ions have in common? So notice that's not a general question about some chemistry knowledge. That's just saying, go look at this picture, these three carbon things, and what are some things that they have in common? So, you know, we can think of a few, I think. If you were here, I would ask you in person, but you can ask yourself. All right, so carbon, let's see, it looks like they all are named carbon. They all have a C as a symbol. They don't all have the same number next to that C because we've got a 12 and then a 13. They don't have the same number of AMU on the bottom here. So the only other similarity is they all have 6 protons. So we could say here, things that they have in common would be 6 protons, the symbol C, and what else did we say? I guess that's it, right? Oh, and they're all called carbon, but I guess that's kind of obvious because they ask us about all 3 carbon atoms. So, you know, you could just leave that there. Now, again, since the goal is for you to actually learn this information, it doesn't matter how specifically you write this thing out. So you can use your own shorthand, you can type it, you can write it, whatever. The goal is to ultimately learn all this information so that whatever works well for you is fine. So then you're going to do the same exact thing with the 4 hydrogen atoms and the magnesium atoms. Go back up and find the same similarities. And what you're going to find is kind of a pattern here. You're going to look for a pattern and you're going to say, oh, wait, I'm seeing kind of the same thing each time. And I'll just tell you, as long as you're here and listening, that if you look at the group of hydrogens, they all also have the same number of protons. If we count them out, 1 for the hydrogens. And the magnesiums also have the same number of protons in 12. So there's this constant, there's the similarity, this pattern throughout these groups of atoms where they all have the same number of protons. So then if we look at a periodic table, which I don't have right here, but, well, I mean, there's one in the classroom, but I will have to load that up on my system for next time. I forgot about that. You can look at what's the significance of atomic number above each element, and you'll see that it actually matches up with that number of protons. So you can see how now you've sort of constructed this idea that the number of protons corresponds to the atomic number. And because you did it by first looking for similarities and patterns, rather than just reading something that said the number of protons is the atomic number, that's going to stick in your head. You're going to learn that and remember that a little bit better. All right, so the whole rest of this packet is like that. You're going to just very literally interpret these questions and write them out, and then ultimately look at these kinds of patterns. So as you step through it, eventually you will get to here, which is wrong. Hold on, don't skip that. That was meant to go down here. I don't know why it got moved, but I'm going to put a different mark here. I'm going to put a star here. That's ultimately what I want you to be able to do at this for this more basic level of atomic structure. So when I say describe atomic structure, I mean if I gave you this symbol, a K with a 40 in the upper left-hand corner, could you fill in all of these blanks and give the atomic number, the mass number, the number of protons, the number of neutrons, the number of electrons, just using that symbol and a periodic table? And the same thing with these other lines. So make sure you can do this and you understand where all those numbers come from. That's something that we'll be looking at the midterm assessment. All right, and then yeah, like this comes from a textbook, so it has some other information that you don't need. All right, so that's the atoms activity, and that should help you get into some atomic structure. Now, if you already know that, if you skip right down to this table and you know exactly how to do all of that, then you may want to move on to something a little bit more in depth to build that understanding. You can try that link to look at some quantum structure. If you have some questions about that, or you want some more information about how to describe the quantum structure of an atom, let me know, and we can definitely talk about that, and I can give you some other stuff to look at, or just we can do another video if there's enough people or a few people interested who want to know more about that kind of thing. We can be very flexible with all of that. Okay. So I said we were going to skip the structures things for right now because that's a little bit more kind of needs its own whole video because it's a big thing. So we're going to jump over to the balancing equations, which is a similar type of exercise, and then we'll talk a little bit more about tomorrow's lab. So you'll notice a similar sort of font and all that. Yes, this comes from the same type of place, and it's the same type of activity where you're going to be kind of learning some things about chemical equations and chemical reactions and what all these things mean. Now that said, I want to go through a little bit more kind of introductory detail about this first. So let's take a look at a chemical reaction that is similar to one that's in this sheet. And it's going to be H2 plus O2 makes H2O. The little G's in parentheses here stands for gas, so that's the state of matter. So this is talking about hydrogen gas, oxygen gas, and then making water vapor when these react. All right, so this is a chemical equation, which is different from a chemical reaction, but sometimes we use them interchangeably. The real difference is a chemical equation is the thing that you write on paper, and a chemical reaction is the thing that you actually do physically in person. So we perform a chemical reaction, and then we describe and write down a chemical equation. So this is a chemical equation, but there's a problem with it. And we discover the problem if we think about what is like actually physically going on here. So instead of just writing these formulas like this, let's actually look at what this would mean. So when we write H2, what we mean is two hydrogen atoms bonded together. We'll talk a little bit about a little more about what that bond, that line means on Wednesday, tomorrow. But it means those two atoms are bonded together. And the O2, same thing. It means those atoms are bonded together. With O, there's this double bond. We'll get into that again another time. And then the water here, the product, is H2O. It's two hydrogens bonded to an oxygen. So if you see that, hopefully you can notice there's a little bit of a problem here because this is meant to be an equation. So if you imagine, these little things kind of coming together and making a reaction, we make a chemical change here, but we've left something out. We've left an oxygen atom out. So if these are the materials on the left that we're starting with, called the reactants, when they do this, there are two oxygen atoms represented here. And then on the right side, there's only one oxygen atom there. So that has somehow disappeared, and that's not okay. The reason that's not okay is because matter is not created or destroyed in a chemical reaction. So something must have happened to that oxygen. There's a few different possibilities. So one is that we just didn't draw it, that there's actually a separate O there. That's wrong because that's not one of the products. I'm saying this is the reaction that happened. No extra oxygen atoms were observed, so we can't just add extra ones. Another thing that sometimes people like to do is change the subscripts and make this H2O2 instead of H2O, because that would actually fit. The reason that doesn't work is H2O2 actually is another compound, that's hydrogen peroxide. And if you've ever experienced hydrogen peroxide, you can probably agree that it is not the same as water, right? So H2O2 is not the same as H2O, so we can't just change the subscripts. So what we're really saying here is that this equation is not balanced, which means that hydrogen and oxygen do not react in a 1-to-1 ratio where one molecule of hydrogen reacts with one molecule of oxygen. Rather, it's going to be in a different ratio, and we have to find that ratio so that it makes it all work out, so that we're not losing or gaining any atoms. For this reaction, since it's fairly simple, we might be able to just notice that if we had a second hydrogen molecule, and then we made a second H2O, that would kind of make it work, because each of the oxygen atoms needs 2 hydrogen atoms to react with it and form water. And that's actually correct. So the way we express that in the chemical equation is by using a large number out in front of the chemical formula, like that. So this tells us 2 hydrogen molecules react with 1 oxygen molecule and end up making 2 water molecules. All right, now this is a balanced chemical equation because we have the same numbers of atoms on each side. Okay, so that's a pretty simple one, but they get a bit more complicated. So let's look at how to do it when they get a little bit more complicated. I wrote down a couple of the examples over here. So let's first take a look at this top one, Fe3O4 plus CO, FeO plus CO2. So now we have a lot of atoms going on, a lot of different things. We can't just necessarily look at those molecules or those formulas and say, oh yeah, I'm going to need 2 of these or 3 of these. It's too complicated. So what we have to do is, what I like to do is just count up each of these atoms on each side. So each side here has Fe, C, and O. On the left, and we're talking about totals of the whole side, we've got 3 Fe's, that's iron, 1 carbon, and 5 oxygens. And then on the right, we've got 1 iron, 1 carbon, and 3 oxygens. We can see that this is indeed not in balance. It is out of balance. All right. So then what do we do to ultimately put this in balance? What we have to do is adjust the ratios, adjust the numbers that are out in front of those reactants. So let's say, all right, so we'll start with iron just because that's the first one we wrote down. We've got 3 on the left and 1 on the right. So we want the same number on each side. So that means that we have to have 3 of these so that we can have 3 irons on each side. So we're going to now correct our inventory so that it reflects the new numbers. So we haven't done anything to the left, that's going to stay the same. But the right side now, we are no longer having 1 iron, we now have 3. And we no longer have 3 oxygen because we changed the number of oxygen also. So now instead of 3 oxygen, we have 3 from here and 2 from here, which is 5. And so if we look across to the other side now, we can see that, oh, that actually brought it back into balance. That's all that we needed to do. We needed to change the amount of that FeO, and now it's all balanced. So that was easy enough. Let's look at this next one. I don't think it's going to go quite as easily. So we'll start the same way. We'll look at our different atoms, CH and O, and we'll count up how many are on each side. So we've got 4 carbons on the left, 1 on the right, 10 hydrogens on the left, 2 on the right, and 2 oxygens on the left, and 3 on the right. Clearly out of balance. Let's start working to bring this in balance. Now one tip here, it doesn't really matter what order you do this in, but if what you do want to do is leave till last whichever atoms are in a bunch of different molecules. So in this example, that would be oxygen. Oxygen is in 2 different molecules on the right, so it's going to be tricky to figure out, like, well, how many of these do I need versus how many of these do I need? So it's easier if we just leave that till the end and hope it works itself out. We'll see what happens. So either carbon or hydrogen we can start with. We started with the top one last time, so let's start with hydrogen this time. Again, it doesn't matter. We've got 10 hydrogen on the left and 2 on the right. So we want 10 on each side because we can't decrease the numbers. So that means we need to put a 5 here. And why a 5 there? Because 5 total water molecules gives us 10 individual hydrogen atoms. because there's 2 hydrogens per water molecule. So now we no longer have 2 hydrogens over here, we have 10. And we no longer have 3 oxygens, we have 5 plus 2, which is 7. Okay. So we're getting closer. Hydrogens are in balance. We're leaving the oxygens till the end. Let's balance the carbons. We've got 4 on the left and 1 on the right. So if we put a 4 here, that's going to change to 4. Oops, I'll keep that over here. And that also changes our oxygen count again. So instead of 7, we have, let's see, 8 from over here, 4 times 2, and then 5, so that's 13. Okay, so carbons are in balance, hydrogens are in balance. All that's left is we need to balance the oxygens. So to do that, we just need to add a coefficient to this oxygen all by itself that will give us 13. So what number can we put here that multiplied by 2 is 13? And guess what? It doesn't work, right? I mean, we could put like 6.5, but you can't really have half a molecule. So that doesn't work. We got an odd number on the right, and we can only go in multiples of 2 on the left. So how are we going to bring that in balance? This is actually a common thing that happens, and I chose this example because it's common, and I wanted to show you that. The easiest way to do it is just double everything else. So instead of 1 of these C4H10s, which is butane, we're going to have 2. Instead of 4 carbon dioxides, we're going to have 8, and instead of 5 waters, we're going to have 10. Double everything, that's going to keep everything else in balance. So if I redo my numbers here, that means I'm going to have double the amount of carbon, double the amount of hydrogen. I haven't messed with the oxygen yet, so we're going to leave that alone. Double the amount of carbon, double the amount of hydrogen, and then this oxygen I did mess with, so now instead of 13, I've got 26. So you'll notice I still have the same number of carbons on left and right, still have the same number of hydrogens on left and right. The only thing now to do is balance those oxygens, and I can do it because now I have an even number on the right. I've got 26. So I can put a 13 here, and that should give us 26 oxygens, and now everything is in balance. So this is telling us that every 2 butane molecules require 13 oxygen molecules to do a full reaction, and then they're going to produce 8 molecules of carbon dioxide and 10 molecules of water. All right, so you can practice those a little bit more here. One of the examples is one we did together, but there's a couple more. This is also something that you can easily find online, practice balancing reactions, balancing equations, and you may not even need to go to that because this week's lab, the chemical reactions lab, will also give you lots of practice of balancing equations. So this is the instructions for this week's lab. You can find it in the labs folder on Teams. Please make sure that you read through this and look up some safety information before lab tomorrow. There's a lot of chemicals, a lot of different stuff going on, so you got to make sure that you're keeping everything straight. There's a good way to set up your notebook because there are clearly delineated like separate reactions. So you can go, okay, we're going to do reaction 1 now, or I guess in here it's called observation. So I'm going to look at my 1, and then because everybody in class is doing this all at the same time, it's really helpful to just skip around. Like, so if somebody's using the observation 1 stuff, you can do the observation 4. So if you've got your observation 4 ready on the next notebook page, then you can just write in what you need there. All right, so we've got what, eight different observations. There's various things that you want to keep in mind in terms of safety here. So we've got magnesium metal in the first one, although this is going to be an instructor demonstration because it is a little bit more dangerous. So if you don't have that in your notebook in terms of safety stuff, that's okay because you're not actually doing it. I'm going to do it. But you actually need magnesium for observation 2 anyway. You've got some 6M, that stands for 6 molar, which is a measure of concentration, hydrochloric acid. So definitely look out for that stuff. Definitely some dangers there. So look that stuff up. Water, candles, you don't have to look anything up like that. Look up some 3% hydrogen peroxide, some potassium iodide. calcium carbonate, again, we're using our hydrochloric acid. You don't have to worry about glucose. And then you do want to look at silver nitrate and sodium iodide. So then, oh, sorry, I'm going the wrong way. So then after the lab, or before if you prefer, you're going to look at the chemical equations for all the different processes that you did in this lab and match them up, which one is which, and then balance them. So these are all unbalanced. Some of them are just balanced as is because they just happen to be balanced on their own, but most of them require some of this balancing that we just talked about. So that will be a good way for you to practice and work through this stuff. So you'll be working in groups of 2 or 3 on this lab. And really, that's a good idea for all of this stuff. So the stuff we talked about before, the atoms activity, the chemical equations activity, if you can get together with people either in person or virtually to kind of work through that stuff together, ask each other's questions, make sure you're understanding it, that can really be helpful. So I really encourage that, that kind of group work, especially the way the class is structured. You need to individually be responsible for learning the material, but you don't necessarily have to, that doesn't necessarily mean you have to write it all out yourself individually. So if you can talk with people about it, if you can learn it together, that can be really helpful. And you don't have to worry about like, oh, I didn't, I didn't get my worksheet done myself, so I'm going to lose points or something like that, because you just need to focus on really understanding the material. All right. Are there any questions in the chat or on Teams here? Doesn't look like it. All right, then I will sign off for now, and I will see you all tomorrow at lab, and then we'll do another class talking about organic structures right after lab. So thanks, everybody.